Hello, everyone. My name is Amir Kermani. I'm a solutions architect at Databricks, focusing in health and life sciences. Today, I would like to talk about how researchers in genomics field are leveraging Databricks to combine different data sources with genomics data and also perform statistical analysis on their data sets at scale. As you know, there's data is being generated with multitude of different data sources are more and more being leveraged in genomic space. For example, we have data from wearable devices, electronic health records, electronic medical records, combined with genomics data sets to inform our science. Genomics data by itself is valuable to a certain degree. However, when the combination with genomics data and phenotypic data is where the real value is. And what we are seeing across the board is that more and more people want to use the same APIs that we are using for analyzing large-scale other data sets to be used with genomics data. So bring that unification to the field. On Databricks platform, actually you can start from the raw data from sequencers and leverage Databricks genomics runtime, which comes with, for example, optimized versions of GATK pipelines, which runs variant calling process on your data set at scale so that you can get from FASTQ to variant calls that can be done in 20 minutes with a comparable cost. So if you really want to get results fast, you can use this pipeline. The other added value is that organically, when you are running this, also the results are automatically written into a data lake. Then you can directly ingest and start analyzing your data using sparse SQL APIs. However, if you don't have that and you already started from VCF, you can then leverage GWAS that I will be talking about to ingest your data and integrate that within your data lake. Also on Databricks platform, genomics runtime, you can run joint genotyping. And joint genotyping, basically, you can have thousands of genomes that you can, by running joint genotyping, you pull information across genomes by informing the population level information, by integrating population level information to increase the accuracy of your variants. They're called variants. And this is a really good example of how you can use the distributed power of Spark to run such workloads. Also, as I mentioned, because we are seeing that more and more people want to use scale and combine data sets, it would be good to bring this kind of standard APIs to the genomics field. So having this motivation, we actually partnered with Genomics Regeneron's Genetics Center to create this open source library called GLOW. So GLOW is a library that is designed to manage tertiary analysis on your data sets from ingest, QC, and downstream GWAS using Spark native APIs. So for example, you can start from VCF, VGen, or Plink files, and ingest that and write that directly into a Delta lake. So Delta is data lake. Databricks created this library, which you can think about it is a data lake that has reliability, performance, and data versioning that you would expect from a data warehouse. So now when you have your data in a Delta lake, you can, for example, query from specific version of your data, which is very important when we are doing anything in science for reproducibility reasons. So as an example of how we are using Delta, how we are using GLOW for ingest, you can start from a VCF file that standard genomics variant data set, and with one line of code, actually you load this VCF into Spark data frame. Now, after you're loading to Spark data frame, you can also display that on Databricks in the tab, display the data frame, and you see that it has this tabular structure already with columns associated with different levels of information that you have in VCF. And also it expands info fields for you as separate columns. And also you have all the genotypes, sample IDs and phase information and the variant codes, etc., in one column. As you see, you can also look at the schema of this table. Now that you have this as a Spark data frame, you can simply interact with this data set the same way that you're interacting with, let's say, any other data set that you have ingested in your data lake. As a matter of fact, you can write SQL point queries against this data set. For example, I want to see how many variants have reference allele A, or even I can have queries on a sample and variant level. As an example of per sample summary statistics, we have specific APIs for that. Let's say I want to look at the summary statistics that I have on a sample level. I'm just writing it, passing these queries in SQL, Spark SQL, and the results that I get are heterozygosity information for each sample, the call rates, etc. And with Databricks, actually, I also, with the notebook environment, I can also visualize these results. For example, if I want to have a correlation between number of deletions and heterozygosity of each individual, I can quickly, interactively visualize that. Similarly, I can look at per variant summary statistics. And in this case, similar to sample level summary statistics, I pass variant level summary statistics query. And I can get, quickly, I can get, for example, allele frequencies for each of these variants and other information. Similarly, I can do other sort of analysis, like, for example, Hardy-Weinberg. These are queries that initially I want to run on my variants so that I can filter some of those variants out for the downstream analysis. So in short, you can use GLOW to ingest your genomics data sets at scale. So the same thing, you can ingest the UK Biobank data. Doesn't matter. If your data set is really large, you just provision a cluster with bigger number of cores to do the ingest. You can write it back in a Delta Lake, optimize that Delta Lake so that you have better performance if you are writing the queries often, which is usually the case. And also you can have data versioning in your Delta Lake. But usually what we are doing all of this analysis is that downstream, we want to do some analysis. Canonical analysis is GWAS, which is genome-wide association studies. Recently, we added a new functionality to GLOW, which is called GLOW-GR. This is built on top of Regeneron's Regeni method, which is the fastest whole genome regression method. And the advantage of this method that we put it in GLOW is that now you can scale your workload, again, by the number of cores that you have. And as this graph shows, that it really, orders of magnitude, decrease in the runtime. What does it translate is that when you're doing a GWAS on a trait, if for a trait it takes days for your GWAS, you can bring it down to hours, so that organically translates, getting faster to your results. Without going into details, this is basically the idea here is that you are going from, in 2 stages this is done. So one stage is you can think about training thousands of models to predict a trait. Then this is actually used for correcting for confounding factors in your analysis, and then you can perform your GWAS. The key here is that all of these steps are linearly scalable, and you can get, which translates to a very good performance. On that note, I stop here. Thank you so much for joining, and I would be happy to answer any of your questions.